No.
Okay, wait a second, please. Now, all right. Now, since we are here, then this is very good. We can go forward now. Okay. Now, there is one graph that I would like to discuss with you, and that graph is related to longitudinal wave and how pressure is changes along with it. So, pressure and longitudinal wave relationship. Okay. Now what happens is that when you see a longitudinal wave, so suppose that this is like, let me just try to, okay, I'll try to, okay, I need to make it bigger. Wait a second, please. Let me make it this way. All right. Now, so consider that this gray area is the compression, okay? And the white part in the middle of these is the rarefaction. All right, now, so this is compression, this is rarefaction, and then compression again, and then rarefaction again, and compression again, like that. So if you plot a wave where you look at the pressure that's happening, because why a compression is created, because the particles are basically being pushed towards the center of compression like this. And why a rarefaction happens is that because the particles go away from it, so that's why there is a gap that happens, right? Like that. Now, because of all this, movement of particles where they're closer and pressing each other, generally what you see is that here the pressure is the highest at the center of compression, and then the pressure is lowest at the rarefaction, and then again high and low and then high, like this. So this would be basically a line that I made where this is pressure and this is basically the displacement, or you can say anything, distance or whatever. So as you can see that the highest pressure is at center of compression, and the lowest pressure is at the center of rarefaction. Understood?
Yes.
Okay.
Yes.
Okay. Now, so do always remember this, all right? Now, so then okay. Okay, I really wanted to do that, but we'll do stationary waves as a single wave. I don't want to, get into that first, because yeah, that would be a bit difficult. All right, never mind. Now, so then today we are going to start off with some more properties of waves, which might be included in your exam as well. So first property of a wave would be the reflection, okay? Now, so when you look at, there is a instrument which we call the ripple tank. Okay, so it looks like this. And the main purpose of a ripple tank is to basically check the behavior of how waves basically behave like this. So it has a tank inside that has water, and you also have an oscillator. It's connected to a motor, and then you have a light. So the waves are generated like this in the ripple tank, and just underneath this you see like lines, like straight lines which are moving like this. Okay, so these are, let's suppose, the water waves right now. This is the light source, and the lines you see right here are the wave fronts. Now, so when you look at a wave front, wavefront can be regarded as perpendicular lines to the direction of wave that connects crests in phase. Alright, let me just show you how. So suppose you have a in a ripple tank or any system, when a wave is created, there are many waves together, they're just not one. Like this, right? All these are the crests of the wave. Same goes here, 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 here. So if you connect them, they are connected by a line like this, as you can see. So this line that I've drawn, these lines, these are the wave fronts, and I've written its perpendicular lines to the direction of wave, which means the wave is basically going in this direction, and they're always 90 degree to the direction of travel of a wave. Is that clear, everyone?
Yeah.
Okay.
Yes.
Quickly draw this, please. Okay, now so what you can do is you can actually do a couple of things through these, and you can first of all display how reflection is done. So on the ripple tank, within that tank, basically we place a barrier like this. Okay, so this is a barrier, and now let's suppose a wave is coming like this. So this would be the incident waves, right? And now the moment it hits the barrier, you're gonna make a normal line. So normal line is basically 90 degrees to the surface, which means it is like 90 degree to the surface where the wave hits, right? So suppose if it hits at this angle, so from the normal to the wave, this angle is I, where I is known as the angle of incidence. Is that clear, everyone?
Yes.
Yes.
Now, then the wave basically reflects at the same angle like this, and this is basically R, and this angle is called the angle of reflection. Okay, so this is just to tell you how it's reflected. And then you can obviously create the wavefronts. The interesting thing about wavefronts are, because they are connected to the crests, so anytime you want to find the wavelength, you can find the distance between two successive wavefronts, and that's when you get the wavelengths. All right, is that clear?
Yes.
Now, there are certain laws of reflection. Oh my god, sorry. The first law of reflection is that the angle of incidence I is always equal to angle of reflection R. All right. Now, the second thing you should remember is that the incident waves and reflected waves stay in the same plane. What I mean by this is, is that, for example, if you look at a 3D plane system like this, right? Oh my goodness, I still didn't change it. That's not fair. Let me just cross it out. So you're looking at a 3D plane system like this, right? So this is X, this is Y, X and Z. So a 3D plane system would be like this, you see. Y would be something like this, okay? This is y-axis, suppose. This is the x-axis, okay? And the z-axis is like this. Uh-oh. Do you guys understand what I'm doing?
Yes.
So what it means is that basically if a wave was supposed to be in the, let me make a small eraser so I can just remove stupid lines. It should be, getting confused here. Okay. I don't want this. Okay, I don't want this. I want this. Okay. So yeah, so if a wave reflects in the x-axis, it will stay in the x-axis. If it reflects on the y-axis, it stays on the y-axis. If it reflects on z, it stays on this. So it can't go like this. It can't go like this. Do you understand? It cannot happen like this. Is that clear to you people?
Yeah.
Okay, very good.
Yes.
Very good. Now, you can draw this, please. It's very important. Now, reflection is like nothing in our syllabus, but refraction is a big part. And refraction is basically bending of a wave when it enters in a different medium that causes a change in speed. So depending on the density of a medium, now, so what happens is that suppose that this is the ripple tank now, and the ripple tank has three different sections. So we got deep, we got shallow, and we got deep. Okay, like that. Now the thing is, suppose that a wave is just traveling like this, it's here. So at this point we're going to draw a normal line. This would be angle I. So what we're going to experience is that when it goes from deep to shallow, the wave basically bends towards the normal like this. Okay, so also we see that if the wave fronts were like these in the deep, now the wave fronts have gone closer to each other, and then when it goes back to deep, if it's the same depth as before, it goes like this. Okay, and then the wavelength increases again. Okay, so this is angle R, this is angle I, this is angle R. So please draw this, and then I'm going to explain to you what it means. I'll be back in just 1 second. All right. Now, you guys are done. Should I go forward now?
Yeah.
Okay. So, now what you guys need to understand is that there are a couple of things happening here. First of all, when it goes from deep to shallow, number one, it causes the wave to bend towards normal, and then also it reduces the speed. Number three, the angle I, which is the incidence, is much greater than angle R. Okay, and fourth thing is the wavelength reduces. Do you guys understand? So that's when it's going
Yeah.
from deep to shallow. Now, and when it goes from shallow to deep, then what happens is that the wave bends away from normal. Number two, it increases the speed, and the angle I is now less than angle R. Also, the wavelength increases. Again, as you can see from the diagram, it is also quite evident. Now, so if I say that this is my medium 1, and let's call this medium 2, the only thing that doesn't change is the frequency stays the same, because the number of waves which enter must also exit, so you expect to have the same frequency. All right, is that clear?
Yeah.
Okay.
Yes.
Cool. Cool. Now, obviously, this bending has to have a certain, way how it bends, and that bending is given us by the Snell's law. So Snell's law explains how much a wave is going to bend when it goes from one medium to another medium, right? So the Snell's law basically is pretty simple, and it says that n1 sine theta 1 should be equal to n2 sine theta 2. Now what these are, let me just explain to you. This n is called refractive index. Refractive index is basically the ratio which is equal to speed of light over the speed of light in the material. All right, is that clear? Now,
Yeah.
let me just show you how. So you can find this by C over V, where obviously this is the speed of light. You should remember the value. It is 3.0 times 10 raised to 8 meters per second. Obviously it's in vacuum or air, and this is the speed of light in whatever medium you're looking at. Now, how Snell's law connect this n by this relationship is that when you look at two different mediums, right? So suppose we are looking at something like, this is the line separating, so there's a wave that enters like this, and this is the normal line that we got to draw every time, and then it bends like this. So this is, suppose, medium 1 and this is medium 2. So every medium has a value of its refractive index, okay? So let's suppose the refractive index of medium 1 is n1 and the refractive index of medium 2 is n2, right? This angle is theta 1 and this angle is theta 2, right? Is that clear?
Yes.
All right. So the value of theta 1 and theta 2 really depends on what the refractive index is going to be. Now, generally, I would just like to tell you a tip that the denser the material is, the higher refractive index would be. What I mean by this is, like, for example, if you look at diamond I believe has a refractive index of 2.4 to 2.8. Depends on what kind of diamond this is. Glass, on the other hand, has a refractive index of 1.5 to 1.7, and water is generally 1.3 to 1.5. Is that clear, everyone? So like that. So the denser it is going to be, the higher the refractive index is going to be. Any questions now? Now let's do
No questions
here. So it says, what is the angle of refraction when light ray passes from water? N is given as 1.33, right? Into glass, which is N is equal to 1.5, hitting the interface between between the two at an angle of 48 degrees to normal. Now remember, the angle is always taken from the normal, okay? Please try to do this. And yeah. Okay. Done? Should I go on now? If you've basically got an answer, please let me know.
I got 1.13.
as an angle. No, that's not possible. Did you do n1 sine theta 1 over n2 sine theta 2?
Okay, I see my mistake.
Okay. Please make sure that your calculators must be in degree mode as well, because sometimes if your calculator isn't, then it would cause a lot of problems for you. Okay, Ikra and Burhan, Safir, Ran, anything?
I got
No, I'm
41.2.
You got what?
I got 41.2 as the answer.
You got 41.2. Yeah. That is correct. That's actually correct. Very good. So what you're going to do is you should do n1 sine theta 1 equals to n2 sine theta 2. n1 is 133 sine 48, right? And then n2 is 1.5 and sine theta 2. So ultimately theta 2 should be 41.2 degrees. Okay. All right.
Yeah.
Now let's go forward, right? Now we are going to look at something called, in fact, let's first draw some of the figures here. Okay. Please wait before you draw anything. Let me finish the drawing and then you can, draw this. Okay. Now suppose we have a glass piece, right? So we're just trying to do a sort of an experiment here to determine critical angle and beyond. So let me just explain how we do it. First of all, we want to have a laser light and we place it at an angle, and the laser light just goes like this, right? Is that clear?
Yes.
Now, so what happens is that this laser light basically goes straight, hits here, And because this is glass, and the light is then going to move in air, because air is less dense than glass, so obviously it's gonna bend away from the normal, right? Is that clear?
Yes. Yes.
Okay. Now, so when it does that, then we can measure this angle I, this R, to see what's happening, and then obviously we can see that as we move the laser light further, like increase the angle of I, just a second please. So then it's like, wait a second please. So if you increase the angle, then what happens is that there will be a time when the angle I, at a certain angle I, the ray is going to completely bend at 90 degrees to the normal, like this. Is that clear?
Yes.
Now, this angle I is called the critical angle. So let's write about critical angle. So critical angle is an angle of angle of incidence at which the angle of refraction is 90 degrees from normal. Do you guys understand this?
Yes.
Good. Now, so to find critical angle, we use sine of C equals to 1 upon n, where this n is the refractive index of medium that it's passing through. Okay, now why is this formula like this? Because there's small derivation here. Let's just do this here. Now we learned that if this is medium 1, right, let's call this n1, let's call this n2. So the medium n1 has a certain critical angle as n, let's suppose, and the theta 1 is C, and the theta 2 is 90, and n2 is basically air. Now just remember that the air's critical angle is just 1. Is that clear? Will you remember this?
Yes. Yeah.
Now if you apply the Snell's law, which is n1 sine theta 1 equals to n2 sine theta 2, then n1 is n and sine theta is sine C, and n2 is 1 and sine is 90. If you take out the calculator and do sine 90, So you'd realize that it's equal to 1, which means that this becomes n times, what did I simply, so this becomes n times sine c equals to 1, hence sine c is equal to 1 over n. Do you guys understand now?
Yes.
Now, the intellectual curiosity of humans would actually let us think that, oh, if even if we go beyond this angle, right? So, like, suppose we move the laser light even further to a larger angle, then what happens is that if this is the angle I, which is much larger than critical angle, so now instead of ray going out, it will reflect back inside at the same angle. Do you understand?
Yeah.
Now,
Yes.
this phenomena is known as the total internal reflection, where total internal reflection means that when the wave reflects back into same medium as the angle of incidence. Okay, I wanted to write the angle. The angle of incidence is greater than critical angle. Do you guys understand this?
Yeah.
Okay. Very nice. Very, very nice. Okay. Now, if you have any questions, please let me know.